Welcome to these gentle, soothing stories for sleep. I am so glad you are here tonight. Whether you find yourself preparing to drift into dreams, seeking a quiet moment of relaxation after a long and challenging day, or simply wishing for a soft voice to accompany you in the stillness, you have found a safe and comfortable place. Tonight, we will begin a journey together. A journey into the deepest and most silent parts of our universe, to ask a question that sounds like it comes from a myth or a legend. Can two black holes merge? We will explore this cosmic dance not as a violent collision, but as a slow, graceful, and inevitable embrace. Before we begin, I would love to know where you are listening from tonight, or perhaps just a word about how your day has been. Please feel free to leave a gentle comment below. Wherever you are in the world, I hope you are feeling comfortable, supported, and ready to explore something truly extraordinary. And if you find these soothing scientific journeys bring you a sense of peace or wonder, please consider liking this video and subscribing to the channel. It helps other souls who are searching for quiet companionship find their way here. Imagine, if you will, the feeling of floating on your back in a perfectly still, boundless pool of water. The temperature is so perfectly attuned to your own that you can barely tell where your skin ends and the water begins. There is no sound, no movement, just a profound sense of weightless calm. Now, imagine feeling a slow, almost imperceptible current begin to stir around you. It is not a forceful pull, but a gentle, pervasive suggestion of movement, a current that seems to be drawing everything, including you, toward a distant, unseen center. This is the oldest sensation in the universe. It is the feeling of gravity. Before we can speak of black holes and their final, silent embrace, we must first settle into a deeper understanding of this fundamental presence, this gentle pull that governs all things. We experience it not as a cosmic drama, but as a constant, quiet companion. It is the comforting weight of a warm blanket on a cold night, the reassuring pressure that tells you the world is solid and real beneath you. It is the feeling of a sleeping cat curled on your lap, a small, warm anchor of trust. We see its work in the graceful, spiraling descent of an autumn leaf, letting go of its branch and dancing on the air until it comes to rest upon the earth. Gravity is the silent author of this reunion, the force that ensures everything that goes up must, in time, gently come down. It holds the atmosphere to our world like a soft, invisible cloak, giving us air to breathe. It holds the oceans in their beds, giving us the rhythmic sound of the tides. It is so constant, so utterly pervasive, that we almost forget it is there at all, much like we forget the sensation of our own breathing until we consciously bring our attention to it. For centuries, our understanding of this force was shaped by the mind of Isaac Newton. He imagined gravity as an invisible universal tether, a kind of instantaneous, magical rope stretching between any two objects in the cosmos. In his mind's eye, the Earth was pulling on the moon with this invisible rope, and the moon was pulling back. This constant, balanced tug-of-war is what keeps the moon in its serene, predictable orbit, preventing it from flying off into the cold darkness of space. This idea was revolutionary, and it painted a picture of a universe as a grand, celestial clockwork, with every planet, moon, and star connected by these unseen threads, their movements all perfectly predictable, if one only knew their positions and the strength of their pull. But then, in the early part of the 20th century, another mind came along and offered an even deeper, more beautiful, and far stranger picture of reality. Albert Einstein suggested that gravity was not a force at all. There was no invisible rope. Instead, he asked us to imagine that space and time were not separate things, but were woven together into a single, dynamic, four-dimensional fabric. Spacetime. He invited us to picture this fabric as a vast, cosmic trampoline, stretched taut and flat in every direction. Now, if you place a heavy object, like a bowling ball, onto the center of this trampoline, what happens? The fabric dips, it curves, it creates a well around the ball. This, Einstein said, is what massive objects like our sun do to space-time. They curve it. Now, if you roll a smaller object, like a marble, nearby, It doesn't fall straight into the bowling ball because of an invisible pull. Instead, the marble begins to circle around the deep well created by the ball, following the curve of the fabric. It is simply moving along the straightest possible path through a now curved reality. This is what our Earth is doing. It is not being pulled by the sun. It is following the straightest possible line through the curved spacetime created by the sun's immense mass. The planets are not puppets on a string. They are coasters on a grand cosmic railway, shaped by the gentle contours of reality itself. And the reach of this effect is infinite. Every single object with mass contributes to this curvature. The Earth creates its own well, which is why the moon orbits us. You, right now, as you lie listening to these words, are creating your own tiny, infinitesimal dimple in the fabric of space-time. Your gravity is technically reaching out to the farthest stars, and the gravity of those distant, ancient suns is reaching back, whispering across the void to touch you. We are all, at this very moment, held in a silent, cosmic conversation, a network of gentle curves and dips on a universal fabric that connects everything to everything else. We are never truly separate, but are held together by this invisible, underlying architecture of the universe. But what happens to this soft, flexible fabric when it encounters an object so heavy, so impossibly dense, that it doesn't just create a gentle dip, but punctures the trampoline entirely, creating a well with no bottom, a fall with no end? Picture the most brilliant star you can imagine, a vast and glorious furnace of light and heat, burning with serene stability for billions of years against the black velvet of space. It is a sun, perhaps 100 times more massive than our own, a titanic sphere of incandescent gas whose life gives warmth and energy to everything around it. Now, imagine watching this ancient, magnificent being as it nears the end of its long life. Imagine it taking its final, shuddering breath before beginning a transformation into something new, something dark, and something eternal. To understand how two black holes might meet, we must first understand this profound moment of their birth, an event that is not an ending, but a powerful and creative metamorphosis. A star's life is a story of a great and perfect balancing act. Deep within its core, the immense pressure and temperature are so extreme that the very atoms of hydrogen are crushed together to form helium. This process, known as nuclear fusion, releases a colossal amount of energy. This energy pushes outwards from the core, a constant, radiant pressure that inflates the star, holding it up against its own crushing weight. It is like a perfectly regulated explosion, a continuous fire pushing out. At the very same time, the star's own immense gravity is trying to do the exact opposite. It is an inward pull, a relentless crushing force, trying to squeeze the entire star down into the smallest possible point. For the millions, or billions, of years of a star's healthy life, these two colossal forces are in a state of perfect equilibrium. The outward push of fusion perfectly balances the inward crush of gravity. The star is a stable, shining beacon, a place of cosmic peace, born from a constant, internal struggle. But this balance cannot last forever, because the star's fuel is finite. As it burns through its hydrogen, it begins to fuse heavier elements in its core. Helium into carbon, carbon into neon, and so on, working its way up the periodic table in a desperate attempt to keep the internal furnace burning. For the most massive stars, this process continues until its core is filled with iron. And iron is a special kind of ash. Unlike all the elements that came before it, the fusion of iron does not release energy, it consumes it. The star has reached the end of the line. The furnace at its heart sputters and dies. In that moment, the outward push of energy that had supported the star for eons simply vanishes. And gravity, which has been patiently waiting, constant and unrelenting, finally wins the battle. The victory is total, and it is instantaneous. With nothing to hold it up, the star's core collapses in on itself with unimaginable speed. In less than a second, a sphere of iron larger than the entire Earth is crushed down to the size of a city, becoming so dense that a single spoonful of its material would weigh more than all the mountains on our planet. The outer layers of the star, which were also being pulled inward, now come crashing down onto this newly formed, superdense core. They hit this unyielding surface and rebound in the most powerful explosion the universe is capable of producing, a supernova. In this titanic blast, the star's outer layers are hurled out into space at nearly the speed of light, enriching the cosmos with all the heavy elements it has forged throughout its life. The gold in a wedding ring, the calcium in our bones, the iron in our blood. All of these atoms were created inside a massive star and scattered across the galaxy by its final, glorious death. This explosion can outshine an entire galaxy for weeks. It is a breathtaking act of cosmic creation. But for the core itself, the story is not over. For the most massive stars, even the incredible density of the collapsed core is not enough to stop the final, ultimate victory of gravity. The collapse continues. The matter is squeezed beyond the point where atoms can exist, crushed past the point where even the nuclei of atoms can hold their shape. According to our current understanding, nothing can stop this final collapse, and the entire mass of the core is squeezed down into an infinitely small, infinitely dense point, a singularity. A new black hole has been born from the ashes of the star. So you see, this process is not one of pure destruction. It is a profound and beautiful alchemy. An ending becomes a new and mysterious beginning. The star's death is not an absence, but a concentration, a distillation of matter and gravity into a new and permanent form of existence. The universe has taken something vast, bright, and ephemeral, and transformed it into something small, dark, and eternal. And now it sits there, in the silent aftermath of the explosion, a perfect sphere of darkness, a scar on the fabric of space-time. What is it like, then, to approach the edge of this newborn abyss, this place where the familiar rules of our reality seem to fray and dissolve at the quiet, invisible precipice known as the event horizon? Have you ever stood at the edge of the ocean on a perfectly clear day, looking out at the horizon where the blue of the water seems to meet the blue of the sky? That line is a horizon of perspective, a limit to your vision based on the curvature of the Earth. It is a gentle, beautiful boundary. In the depths of space, there exists another kind of horizon, one that is not a limit of perspective, but a fundamental limit of reality itself. It is the shore of an ocean from which no traveller can ever return, a quiet, dark line drawn around a place of unimaginable gravity. As we imagine our journey continuing from the birth of the black hole, we now approach this mysterious boundary, the event horizon. The silence here is more profound than any you have ever known. It is not merely the absence of sound, but the absence of the possibility of sound. The starfield around you begins to behave strangely. The light from distant suns, which should be sharp, steady points, begins to warp and bend as if you are looking at them through a vast, invisible lens. The constellations you once knew become distorted and unrecognizable, their light smeared into strange arcs and circles, and you feel a strange sense of lethargy, as though time itself has become thick and viscous, like you are trying to move through cool, clear honey. Each thought, each movement, feels as though it takes an eternity to complete. This is the realm where the normal rules of the universe begin to stretch and break. To understand this boundary, we must first think about a simple idea called escape velocity. Here on Earth, if you throw a ball into the air, gravity pulls it back down. But if you could throw it fast enough, at a speed of about 11 kilometers per second, it would have enough energy to overcome Earth's gravity completely and fly off into space, never to return. That speed is Earth's escape velocity. Every object in the universe has one. The more massive and dense the object, the higher its escape velocity, because its gravitational pull is stronger. For a dense star like a neutron star, the escape velocity might be half the speed of light. Now, a black hole is the result of matter being crushed to a point of theoretically infinite density. Its gravity is so powerful that, at a certain distance from its center, the escape velocity becomes equal to the speed of light. And since the laws of our universe state that nothing, absolutely nothing, can travel faster than the speed of light, this distance marks the ultimate point of no return. This is the event horizon. It is crucial to understand that it is not a physical surface. It is not a wall you would crash into or a membrane you could touch. It is a purely geometric boundary, a one-way door in the fabric of space-time. If you were to cross it in a spaceship, you might not even notice the exact moment you passed through. There would be no bump, no flash of light. But once you were across, your fate would be sealed. All paths, all possible futures, would lead in only one direction, toward the singularity at the center. The gravity is so extreme that it has warped space-time to the point where outward is no longer a direction you can travel in. The beautiful and strange distortion of the stars we imagined earlier is a direct consequence of this extreme warping of space. It is a phenomenon known as gravitational lensing. The black hole's immense gravity bends the path of light, just as a glass lens bends light to magnify an image. Light rays from a distant star that would normally travel in a straight line far past the black hole are instead captured by its gravity and bent toward our eyes. This can create multiple images of the same star, or stretch a star's light into a perfect circle, known as an Einstein ring, if the alignment is just right. The event horizon itself acts as a perfect silhouette against this warped background, a circle of pure blackness from which no light can emerge. It is the shadow that this object casts upon the cosmos. In this way, the event horizon represents more than just a physical boundary. It is a boundary of knowledge itself. It is a veil beyond which we cannot see, a place where our most powerful telescopes and our most brilliant theories are met with perfect, impenetrable silence. It reminds us, in the most profound way, that some mysteries may be fundamental to the nature of the universe, that there are shores of reality upon which our understanding may never be able to land. This profound warping of light, however, is just a symptom, a visible clue to a much deeper truth. The black hole is not merely an object existing in space. It is an object that has fundamentally changed the very nature of space and its inseparable partner, time, all around it. We often think of time as being like a clock, an impartial and universal metronome, ticking with a rigid and relentless precision, the same for everyone, everywhere. 1 second on Earth is 1 second on Mars is 1 second in the most distant galaxy. But this idea, as comforting as it is not the deepest truth. What if, instead, we imagine time as being more like a great and mighty river, a river that flows through the cosmos, with its own currents, its own gentle eddies, and its own thundering waterfalls? This is the universe that Albert Einstein revealed to us, a universe where time is not a rigid ruler, but a fluid and flowing dimension of reality. Let us rest for a moment in this sensory image of a river. Imagine you are in a small boat. In the center of the river, where the water is deepest, the current is swift and strong, carrying you along at a steady pace. But as you paddle closer to the riverbank, you notice the water moving more slowly, held back by the friction of the land. If you drift behind a large boulder, you might find yourself caught in a gentle swirling whirlpool, an eddy where the water seems to turn back on itself. These different flows, these currents and eddies, are a beautiful and accurate metaphor for how space-time itself behaves in the presence of massive objects. The river is space-time, and the gravitational pull of planets and stars acts like the riverbanks and the boulders, altering its natural flow. Einstein's revolutionary insight was that space and time are not two separate arenas. They are inextricably linked, woven together into a single, four-dimensional fabric he called space-time. You cannot move through space without also moving through time, and you cannot alter the fabric of space without also altering the flow of time. This led to a remarkable prediction. Gravity affects the passage of time. This effect is known as gravitational time dilation. Just as the river of water flows more slowly near the bank, the river of time flows more slowly in a stronger gravitational field. Near a massive object like a star or a black hole, the river of time becomes sluggish and deep. A clock placed near the event horizon of a black hole would tick much more slowly than a clock far away in the emptiness of space. This is not a theoretical fantasy. It is a measurable reality of our universe. The very GPS satellites that orbit our Earth, which we use for navigation every day, have to account for this effect. Because they are in a slightly weaker gravitational field than we are on the surface, their clocks tick just a tiny fraction of a second faster than ours. If our engineers did not constantly correct for this subtle time difference, our navigation systems would become inaccurate by several kilometers every single day. For a normal star, this effect is subtle. For a black hole, It is profound. But the strangeness does not end there. If a black hole is spinning, it does something even more bizarre to the space-time around it. It doesn't just curve it. It twists it. Imagine placing a large, spinning ball into a vat of thick honey. As the ball spins, it doesn't just sit there. It drags the honey around with it, creating a swirling vortex. A spinning black hole does exactly this to the fabric of space-time. This effect is called frame dragging. It creates a cosmic whirlpool, a region of space where you cannot stay still, no matter how powerful your rocket engines are. Space itself is in motion, flowing like a vortex around the black hole, and you are forced to be carried along for the ride. This is the true power of these objects. They do not just exist within the universe. They command the very stage upon which the universe unfolds. And perhaps this physical reality of the cosmos finds a faint, gentle echo in our own minds. Our personal perception of time is also wonderfully fluid. A single, joyful afternoon with someone we love can fly by in what feels like only a few precious moments. Yet a single moment of deep anxiety or fear can seem to stretch on for an eternity. Athletes and artists often speak of a flow state, a period of intense focus where time seems to slow down, allowing them to perceive and react with extraordinary clarity. Perhaps our consciousness, in its own small way, contains a memory of the universe's great, flowing river of time. If just one of these silent, solitary objects can command the currents of reality in such a profound way, what could possibly happen when two of them, two lonely wanderers, each surrounded by its own deep and swirling storm in space-time, begin to feel each other's presence across the dark? Imagine a being, a consciousness, that has drifted through the silent, velvet darkness of the cosmos for millions, perhaps even billions, of years. Its path is not chosen, but is guided only by the faintest, most subtle gravitational whispers from unseen stars and distant, ghostly galaxies. It is a wanderer, a pilgrim on a journey of unimaginable length and solitude. This is the life of a black hole, a lonely traveller moving through the great, quiet emptiness. Let us follow one on its journey. For millennia, it glides through the cold, diffuse gas that lies between the stars. Then, its path takes it into a vast nebula, a stellar nursery of breathtaking beauty. It passes like a shadow through clouds of incandescent hydrogen that glow with a soft rose-coloured light, and through shimmering veils of blue and violet dust, where new suns are just beginning to ignite. It feels the gentle gravitational tug of these newborn stars, and they, in turn, feel its immense presence, their paths subtly altered by its passage. But it does not stop. Its journey continues, carrying it out of the nebula and into a dense, ancient star cluster. Here, the stars are packed together like a swarm of brilliant diamonds, their golden light bathing the wanderer in a constant, silent glow. Yet still, it is a place of profound loneliness, for though it is surrounded by light, it shares none of its own. It is a ghost at the feast of creation. And then, its long, arcing path carries it away from the cluster, out into the near-perfect vacuum of intergalactic space, a darkness so profound and an emptiness so vast that the journey to the next island of light will take 100 million years. This image of a solitary wanderer is not merely a poetic fancy. It is a physical reality. Black holes are not stationary monuments in the cosmos. They are born from massive stars, and those stars were almost always part of a larger system, a galaxy filled with other stars, all moving in a great, coordinated rotation. So, when a star collapses, the black hole it creates inherits all of that momentum. It continues to orbit the center of its home galaxy, just as its parent star once did. Sometimes, however, a black hole is not born alone. Many massive stars, in fact most of them, are not single points of light like our own sun. They are born in pairs, as binary systems, two great stars locked in a graceful, gravitational waltz around a common, empty center. They live their lives together, orbiting one another for millions of years. And if both of these stars are massive enough, they will both end their lives in the same way. In the fiery blast of a supernova, leaving behind a black hole. What remains is a binary black hole system, two dark wanderers, already bound together by gravity, continuing their silent dance. They may be separated by a great distance at first, their orbit taking thousands of years to complete, but their fate is already written. They are companions on a long, slow journey that can only end in one way. And sometimes, the journey to find a partner happens on a scale that is difficult for the human mind to even hold. Our universe is filled with galaxies, great islands of stars, and sometimes these islands collide. Over hundreds of millions of years, two galaxies can pass through one another, their stars rarely hitting, but their structures merging and rearranging under the mutual pull of gravity. At the heart of each of these galaxies lies a supermassive black hole, millions or billions of times the mass of the Sun. As their host galaxies merge, these two giants, once the quiet hearts of their own separate domains, are now set on a long and ponderous collision course. They begin a new dance, the slowest and most majestic of all, a spiral toward one another that will itself take many more millions of years to complete. Whether they are born as companions or find each other after eons of solitary travel, the story of these wanderers raises a gentle question. Is there a form of cosmic awareness in this profound solitude? A quiet, patient existence that spans ages we can barely comprehend. Perhaps this long, silent journey through the void mirrors our own passage through life. A slow drift through the years, a quiet search for connection, until, one day, our path finally and fatefully intersects with another. For two of these wanderers, separated by a vast gulf of space but now bound by an invisible thread of gravity, how do they first signal their presence to each other? The first message is not sent through light, for they have none to share. It is sent through a tremor, a faint and ancient vibration, in the very fabric of reality itself. Have you ever stood on a quiet country road and felt the faint, deep vibration of a distant train through the solid ground beneath your feet, long before your ears could pick up the faintest sound of its approach? The earth itself carries the message, a low-frequency tremor that speaks of a great energy on the move. The universe communicates in a remarkably similar way. Its grandest and most powerful events do not announce themselves with a flash of light or a crash of sound, but with a silent, invisible tremor that travels not through the ground, but through the very fabric of space-time. These tremors are called gravitational waves. To truly feel what they are, let us return to our image of space-time as a vast, cosmic pond, its surface perfectly still and mirror-smooth. Every single movement, every event in the cosmos, creates a ripple on the surface of this pond. A planet orbiting its star creates a continuous, gentle, repeating wave. A star that explodes in a supernova creates a sudden, chaotic splash. Most of these ripples are infinitesimally small, so faint that they are lost in the quiet background of the universe. But the ripples from the most powerful events can travel for billions of years, across unimaginable distances, to finally wash up on our distant shore. Imagine, right now, in the quiet room where you are listening, that one of these ancient ripples is passing through you. It is a wave that has traveled for perhaps 1 billion years, since a time before complex life even existed on Earth, sent on its way by the dance of two distant black holes. As this wave of space-time moves through you, it is subtly altering the very geometry of the room. First, it gently stretches the space, so that the distance between the floor and the ceiling grows by a truly minuscule amount, while the distance between the walls on your left and right shrinks. Then, a moment later, it does the opposite, compressing the vertical space and stretching the horizontal. This stretching and squeezing of reality itself is happening continuously, as a constant soft rain of gravitational waves from all across the universe washes over our planet and everything on it. The effect is so impossibly small, far, far smaller than the width of a single atom, that for all of human history, we were completely unaware that it was happening. We were like creatures living at the bottom of a deep, calm ocean, completely oblivious to the gentle, slow-moving currents all around us. This idea was first predicted by Albert Einstein a century ago, a natural consequence of his theory of general relativity. He reasoned that if massive objects curve space-time, then accelerating massive objects should create waves, or ripples, in that curvature. He understood that anything with mass that accelerates you, when you wave your hand, the Earth, as it orbits the Sun, must be creating these waves. But he also calculated that the energy these waves carried away would be so tiny that we would likely never be able to detect them. For a century, they remained a beautiful but unproven prediction. To make a gravitational wave that is powerful enough to be detected, you need an event of truly cosmic violence. You need immense masses, far greater than our Sun, moving at speeds approaching the speed of light. You need a cosmic symphony, not a solo instrument. The perfect source, the universe's most powerful gravitational wave generator, is a pair of black holes locked in the final, frantic moments of their orbital dance. So, the universe is not the silent, still place it appears to be on a dark night. It is humming. It is filled with the echoes and reverberations of ancient, powerful events. It is a constant chorus of gravitational waves, telling the stories of colliding stars, merging black holes, and perhaps even the faint, residual tremor of the Big Bang itself. We are, in a very real and physical sense, swimming in an ocean of cosmic memory, a universe that is constantly whispering the tales of its own dramatic past. As our two lonely black holes, our cosmic dancers, draw ever nearer to one another, their slow waltz begins to quicken. And as they move faster and closer, whipping around each other with increasing speed, these gentle, background ripples they have been making begin to grow into powerful, focused waves, carrying a clear and undeniable message of their impending, final union. Have you ever watched two dancers on a grand, dimly lit stage, slowly circling one another at a great distance? They do not touch, but their movements are perfectly synchronized, a silent conversation of graceful motion. Then, as the music swells, their orbits begin to grow tighter with each pass, a sense of beautiful, slow-motion tension building as they are drawn, inevitably, toward the center of the stage for their final embrace. In the vast, dark theater of the cosmos, gravity provides the silent music for a similar, and far more ancient, dance. This is the in-spiral, the long and elegant journey of two black holes, spiraling toward their union. Let us try to visualize it. We see them from a great distance, two perfect spheres of absolute darkness, two holes in the fabric of reality, orbiting a common, empty center. At first, their dance is impossibly slow. They might be as far apart as a star and its planet, taking hundreds or even thousands of years to complete a single, majestic orbit. For eons, they move with this patient, stately grace, their presence known to each other only through the gentle curvature of the spacetime that separates them. As we move closer in our imagination, or perhaps as we let the cosmic clock run faster, we see the pace of their waltz begin to change. The distance between them shrinks, and their orbit tightens. They are now closer than the Earth is to the Sun, and their orbital period has shortened from centuries to mere hours. The dance is becoming more intimate, more urgent. This long period, this slow and graceful tightening of the spiral, is the heart of our story. But what is the mechanism that drives it? Why do they get closer at all? If gravity is just holding them in orbit, like the Earth around the Sun, shouldn't they be able to continue this dance forever? The reason they cannot is because their dance is not perfectly silent. As we discovered, their immense masses, whipping around each other at incredible speeds, are constantly churning the space-time around them, sending out those faint but persistent ripples, the gravitational waves, and these waves carry energy. Every ripple that flows outward is a small amount of orbital energy being radiated away from the system, lost forever into the vastness of the cosmos. It is a slow, relentless leak of the very energy that is keeping them apart. We can think of it like a beautiful, intricate, spinning top, set in motion on a tabletop. At first, it spins with a fast, stable hum. But the friction with the table and the resistance of the air are constantly draining its rotational energy. As it loses energy, it begins to wobble, its spin slows, and it eventually comes to rest. For the two black holes, the emission of gravitational waves is a kind of perfect, frictionless resistance. The constant, unending broadcast of these waves drains their orbital energy, forcing them into a lower and therefore tighter orbit. And this process, this slow gravitational bleeding, is what makes their final union not just a possibility, but an absolute inevitability. It is a one-way path. The more energy they lose, the closer they get. The closer they get, the faster they orbit. And the faster they orbit, the more powerful the gravitational waves they emit, which causes them to lose energy even faster. It is a feedback loop, a runaway process that is slow for eons and then becomes unimaginably fast at the very end. In the final minutes of their billions of years-long dance, the two black holes are no longer moving with a stately grace. They are a blur of motion, separated by only a few hundred kilometers, whipping around their common center hundreds of times every single second. They are moving at a significant fraction of the speed of light, pushing the laws of physics to their absolute limits. Their fate, which was written in the laws of gravity the moment they were bound together, is now just moments away from being fulfilled. They must merge. This celestial dance speaks to the very nature of inevitability. Some paths in our universe, and perhaps in our own lives, once taken, lead to a single, inescapable conclusion. The beauty, then, lies not only in the destination, but in the journey toward it, in the long, graceful, and patient spiraling path to a final, profound unity. But if we could somehow translate the ever-intensifying energy of these gravitational waves into a medium our own senses could perceive, what would this final, frantic stage of the cosmic waltz sound like? I invite you now, if you feel comfortable, to close your eyes. Take a slow, gentle breath and listen to the silence around you. The soft hum of the air, the distant sounds of the world outside. Now, from the very deepest part of that silence, imagine you begin to hear the faintest, lowest rumble. It is a sound so deep it is more of a feeling, a vibration in your chest. It is a sound that has been traveling across the empty oceans of space for over 1 billion years. A message from a time long before our human ancestors walked the earth. A sound that has finally, at this very moment, arrived here to tell its story. As you listen, this deep, cosmic bass note begins to slowly rise in pitch. What was a rumble becomes a low hum, then a clear, audible tone. The tone continues to climb, getting louder and higher with each passing moment. Whoop, 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 each cycle faster than the one before it. It is the sound of two of the most massive objects in the universe, tearing the fabric of space-time apart, faster and faster and faster. The tone soars upwards into a high-pitched cry, a crescendo of impossible energy, before it suddenly, abruptly, stops. And the silence that follows is even more profound than the silence that came before. You have just heard, in your mind, the sound of two black holes merging. For a century, this sound was only a prediction, a whisper in the mathematics of Einstein's equations. But we have now built an observatory capable of hearing it. It is not a telescope that gathers light, but a cosmic microphone that listens for the vibrations of space-time itself. It is called LIGO, the Laser Interferometer Gravitational Wave Observatory. Its design is both incredibly simple in concept and breathtakingly complex in execution. Imagine two long, hollow tunnels, each 4 kilometers in length, arranged in the shape of an L. A powerful laser beam is split in two, and one half is sent down each tunnel. At the end of each tunnel is a perfect mirror, which reflects the laser light back to the corner where it started. The lengths of the tunnels are so precisely controlled that when the two laser beams return and recombine, they are perfectly out of step with one another, and they cancel each other out completely. So, a light detector placed at that corner sees only darkness. But, when a gravitational wave passes through the Earth, it stretches one of LIGO's arms and simultaneously squeezes the other. For a fleeting moment, one tunnel is slightly longer and the other is slightly shorter. This minuscule change means the two laser beams no longer travel the exact same distance. When they return to the corner, they are no longer perfectly out of step, and they no longer cancel each other out. A tiny flicker of light reaches the detector. That flicker is the signal. That is the sound. The reason it sounds like a rising tone is because of a simple relationship between speed and sound. Just like a sound wave, a gravitational wave has a frequency, which is the number of wave crests that pass by in a single second. Our ears interpret frequency as pitch. A low frequency is a low note. A high frequency is a high note. As the two black holes spiral closer together, they orbit each other faster and faster. This faster orbit generates gravitational waves with a higher and higher frequency. So, as we listen, the pitch of the signal rises in perfect lockstep with the accelerating dance of the black holes. This is why scientists gave the signal its wonderfully simple name, the chirp, because when we take the raw data from the detector and convert it into a sound file in the range of human hearing, it sounds exactly like the quick, rising chirp of a bird. On September 14th, 2015, for the first time in human history, the two LIGO detectors, one in Louisiana and one in Washington state, both recorded a clear, unmistakable chirp that had traveled for 1.3 billion years to reach us. For all of our existence as a species, we have looked out at the universe in silent wonder, seeing its light but never hearing its voice. On that day, everything changed. We are no longer just seeing the cosmos. We are listening to it. We are hearing the echoes of events so powerful and so distant that they connect us to the universe in a new and profoundly fundamental way. It is the universe's own music. And while we hear this celestial song from the safe harbor of our world, a billion years after the performance has ended, what is the experience of time itself for the two dancers caught in the very heart of the storm as their final moment approaches? If you could, for a moment, imagine yourself as a silent observer in a perfectly safe spaceship, hovering at a respectful distance from this final cosmic performance. If you were to look at the two black holes through your viewport, you would see something utterly strange, something that seems to defy all logic. You would know, from the powerful gravitational waves your ship is detecting, that the two objects are whipping around each other in a frantic, final blur, completing hundreds of orbits in a single second. And yet, what your eyes would see would be something else entirely. The dance would appear to be unfolding in an exquisite and graceful slow motion. Each movement would seem deliberate, languid, as if the two cosmic dancers had all the time in the world. This is perhaps the most profound and dreamlike aspect of their final embrace. For those caught within it, time itself loses its familiar rhythm. Let us try to hold this strange, dual perspective in our minds. From our distant, safe vantage point, we are the objective audience. We see the system as a whole, a furious storm of space-time, a blur of motion radiating immense energy. Our clocks, aboard our ship, tick at their normal, steady pace. But if we could use a magical telescope to zoom in on a hypothetical, indestructible clock that was somehow attached to the edge of one of the black holes, we would see its second hand moving with an agonizing slowness. Each tick would, to us, seem to take minutes, then hours, then an eternity. While from our perspective their dance is a frantic finale, from their own perspective, time is stretching out, becoming impossibly deep and slow. This is the effect of extreme gravitational time dilation, which we touched upon earlier. In the final moments of the merger, the gravitational field becomes so incomprehensibly intense that the river of time, for the black holes themselves, slows to a near-perfect standstill relative to the rest of the universe. This raises a fascinating and gentle question. Whose time is the correct time? Is it our fast, steady clock, or their slow, syrupy one? And the beautiful revolutionary answer that Einstein's theory of relativity gives us is that both are correct. There is no single, universal, master clock for the cosmos. Time is not absolute, it is relative. It depends entirely on your motion and on the strength of the gravity you are experiencing. The black hole's experience of their final moments unfolding is just as physically valid as our experience of watching them. They are simply living, for a brief and final moment, in a completely different temporal reality, a different rhythm of existence. And perhaps, in a very faint and poetic way, we have a small taste of this in our own lives. Our psychological experience of time is also wonderfully elastic. Think of an athlete, in the zone, making a game-winning play. They often report that in that crucial second, Everything seemed to slow down, giving them all the time they needed to see, to plan, and to act with perfect precision. Or a musician, lost in the rapture of a complex solo, feels as though they have an eternity between each note. In moments of intense focus, or even in moments of sudden, shocking danger, our minds seem to have the ability to stretch our perception of a single moment. It is a subjective, internal echo of a deep and fundamental physical law of the universe. So, as we watch this silent, slow-motion drama unfold, we are reminded that time is not the rigid, unyielding framework we so often perceive it to be. It is a flexible, flowing dimension of reality, a river that can run fast and shallow in one part of the universe, and deep and slow in another. This cosmic event, this final waltz, reveals that our own steady, day-to-day experience of time's passage is just one perspective, one current, in a vast and varied cosmic ocean of infinite temporal rhythms. As they move at these impossible, blurring speeds, slowed in our vision only by the strange and beautiful stuttering of time itself, they are racing against the one fundamental speed limit of the cosmos, a barrier they can get tantalizingly close to, but can never, ever break. Imagine you are running a race, your heart pounding, your legs moving as fast as they possibly can. You can see the finish line ahead of you, a clear and steady goal. But now, imagine something strange begins to happen. The faster you run, the faster the finish line seems to move away from you. If you double your speed, the finish line doubles its speed too, always staying just out of reach. No matter how much effort you exert, you find you can never quite get there. For every object with mass in our universe, the speed of light is that ultimate, unreachable finish line. It is a fundamental law of the cosmos, a barrier built into the very mathematics of reality. As our two black holes enter their final, frenzied dance, they are running this impossible race, pushing this cosmic speed limit to its absolute extreme. Let us take a moment to feel what this limit might be like. We know the sensation of speed in our everyday lives, the rush of wind as we ride a bicycle, the blur of the landscape from the window of a fast-moving train. Now, let us imagine we are in a spaceship, accelerating continuously, moving faster and faster. At 90% of the speed of light, the universe outside our window would begin to look very strange. The stars in front of us would appear blue-shifted, their light compressed into higher energies, while the stars we leave behind would look red-shifted, stretched into the deep, cool colors of the spectrum. At 99%, the effect would be more profound. The universe would seem to funnel into a narrow tunnel of light ahead of us, and our own personal experience of time would slow to a crawl compared to the universe we left behind. For every year that passed for us on our ship, decades or even centuries could be passing on Earth. And as we pushed our engines even harder, trying to gain that last 1%, we would find it took more and more energy for less and less gain in speed. The finish line would be right there, but we would never be able to cross it. The reason for this is one of the deepest and most elegant truths about our universe, discovered by Einstein. He realized that the speed of light in a vacuum, a value we call car, is constant for all observers. This sounds simple, but it is a revolutionary idea. It means that whether you are standing still or flying towards a beam of light at half the speed of light yourself, you will always measure that beam of light to be moving at the exact same speed. The only way the universe can conspire to make this true is if our experiences of space and time are themselves flexible. But it also leads to his most famous equation, E equals mc squared. We often hear this as meaning that matter can be converted into energy, but it also means something more subtle. It tells us that mass and energy are two sides of the same coin. Mass is a form of concentrated, resting energy. As you accelerate an object with mass, the kinetic energy, the energy of its motion, actually adds to its total effective mass. So, as an object approaches the speed of light, its mass begins to increase from the perspective of an outside observer. Its inertia, its resistance to being pushed, grows larger and larger. As its speed gets infinitesimally close to the speed of light, its effective mass approaches infinity. And to accelerate an object of infinite mass, you would need an infinite amount of energy. This is why the speed of light is the ultimate speed limit. Our two merging black holes, in their final moments, are a perfect illustration of this cosmic law. They have mass, and therefore they can never reach the speed of light. But in the final fractions of a second before they touch, they are moving at more than half this ultimate velocity, over 150,000 kilometers every single second. They are converting their orbital energy into gravitational waves with an efficiency that dwarfs any process we know on Earth, pushing the very limits of what is physically possible for objects of such immense mass. These universal laws, like the speed of light, are not cages designed to limit the universe's creativity. Instead, they provide the fundamental structure, the rules of the game, within which all of the beautiful and complex cosmic creativity can unfold. The speed of light is not a prison wall. It is the canvas on which the entire dance of matter and energy is painted. So, with time stretched to a breaking point for the dancers, and the cosmic speed limit looming just beyond their grasp, what happens in that final, infinitesimal fraction of a second, when these two shores of eternity, these two masters of gravity, finally and physically touch? Imagine, if you will, two perfect, shimmering soap bubbles, floating gently towards each other in the still air of a quiet room. You watch as they drift closer and closer, their iridescent surfaces reflecting the soft light. Then, in a single, silent, and magical instant, they touch. Their individual boundaries dissolve, and where there were once two, there is now one single, larger bubble, wobbling and trembling, its surface oscillating as it tries to find a new, stable, spherical shape. This gentle, beautiful image is the closest our everyday world can offer to the silent, climactic moment when two black holes finally touch. Their final union is not an explosion of fire and shrapnel, but a silent, violent reformation of the very geometry of reality. As the two event horizons, two perfect spheres of absolute blackness, race toward each other in their final millisecond, the intense gravity begins to distort their shapes. They stretch into teardrops, their pointed ends reaching out for one another. And then they touch. A thin, dark bridge of spacetime forms between them, a place where the two separate regions of no return have now become one. This bridge does not linger. It expands with breathtaking speed, and in an instant, the two individual event horizons have vanished, replaced by a single, continuous, but wildly distorted and misshapen surface. For a fleeting moment, there is a single, peanut-shaped object of pure blackness, a wobbling, unstable vessel that contains within it the unimaginable chaos of two cosmic titans becoming one. This is the moment of merger, the creation of a common event horizon. From this instant forward, anything that happens within this new, larger boundary is sealed off from the rest of the universe forever. It is the closing of a final, cosmic curtain on the lives of the two individual black holes. And inside this new, private universe, the final act of the drama unfolds. The two singularities, the points of theoretically infinite density that were the original hearts of the two black holes, are now trapped together within the same prison. They begin a final, chaotic plunge, a relativistic death spiral toward each other that our current laws of physics are not yet equipped to describe. This is the place where Einstein's beautiful theory of general relativity, which has guided us so perfectly on our journey so far, finally admits its limits and falls silent. We do not know what happens when two singularities merge. It is one of the deepest and most profound mysteries in all of science, a question that likely awaits a new revolution in our understanding of reality, a theory of quantum gravity. But while the events on the inside are a mystery, the behavior of the new, shared horizon on the outside is something we can describe. And it is a thing of beautiful, temporary imperfection. There is a profound principle in physics known as the no-hair theorem. It states, in essence, that a stable, settled black hole is the simplest object in the universe. It has no mountains, no valleys, no complex features of any kind. It can be perfectly described by only three properties: its mass, its spin, and its electric charge. It has, metaphorically, no hair. But this newly born object, this trembling, peanut-shaped union, is messy. It is lumpy. It has distortions and asymmetries. It is, for a brief moment, a hairy black hole. This is an agitated, unstable state, a momentary violation of the universe's preference for elegant simplicity. The laws of physics demand that this new object cannot remain this way. It must shed all of its complex imperfections, all of its hair, and settle into its final, pure, and simple form. This is a moment, then, of pure, unadulterated chaos, but a chaos that contains within it the absolute necessity of finding a path toward perfect simplicity. The universe, even in its most violent and extreme moments, seems to possess a deep and abiding impulse to smooth out complexity, to erase the scars of a violent birth, and to return to a state of profound and simple equilibrium. But this new, trembling entity, ringing with the memory of its own creation, cannot just wish its imperfections away. Like a bell that has just been struck by a mighty hammer, it must radiate this violent, chaotic energy outward, broadcasting the story of its birth in a final, glorious song. Have you ever had the chance to stand close to a very large, deep-toned bell just after it has been struck? In the first instant, there is an almost overwhelming clang, a chaotic mix of sounds and vibrations. But that initial, deafening noise quickly fades, and what is left behind is a pure, beautiful, and resonant tone. A single clear note that shimmers in the air, slowly and gracefully fading into silence. The newborn black hole, in the moments following its chaotic creation, does something remarkably similar. It sings a final silent song to the universe, a song of pure gravity. Let us visualize this moment of calming resolution. We see the distorted, misshapen black hole, still trembling from the violence of the merger. Its surface, the newly formed event horizon, is not smooth, but is covered in ripples and oscillations, like a pool of impossibly black water that has been deeply disturbed. These vibrations are not random. They are a clear, harmonic quiver. With each pulse, the black hole's shape becomes a little smoother, a little rounder, its gravitational field a little more uniform. It is shedding its imperfections, shaking off its hair, and with each quiver, it radiates away this excess energy in a final, powerful, and beautifully clear burst of gravitational waves. This process, this calming of the storm, is known as the ring down. It is the final, beautiful act of the merger, the moment when the newly formed, agitated black hole settles into its final, eternal state of placid equilibrium. It is the cosmic equivalent of the bell's pure fading tone. And just as the sound of a musical instrument is not just a random noise, the gravitational waves of the ring down are not random either. They are a specific and predictable set of frequencies, a kind of gravitational music. Physicists call these frequencies the quasi-normal modes. They are like the harmonic overtones of a plucked guitar string. When you pluck a string, you hear the main, fundamental note, but you also hear a faint series of higher, purer notes that give the instrument its unique character, its timbre. In the same way, the ring down of a black hole is a chorus of gravitational tones. And here is the most beautiful part. The exact frequencies of these tones, their pitch, and the rate at which they fade away are determined by only two things: the mass and the spin of the final, settled black hole. They are a unique and unmistakable fingerprint of the new object. This allows scientists to perform one of the most powerful and elegant tests of Einstein's theory of general relativity ever conceived. From the chirp of the in-spiral, they can calculate what the mass and spin of the final black hole should be. Then, they can independently listen for the ring of the ring down that follows, and measure its quasi-normal modes. If the tones of the ring down perfectly match the pitches predicted by the chirp, it is a stunning confirmation that Einstein's theory holds up, even in this most extreme and violent environment in the known universe. And in every single merger we have observed, the match has been perfect. We are not just hearing a story, we are hearing a story that unfolds exactly as our deepest understanding of gravity predicts it should. In this, we can find a sense of profound comfort. The universe, even in its most chaotic moments, is not arbitrary. It follows deep, elegant, and understandable laws. The ring down shows us a universe with a deep and powerful impulse towards equilibrium. After the most profound violence, there is a natural, inevitable process of settling, of finding a new and stable peace. It is a cosmic model for healing, a slow and graceful release of turmoil and trauma, until a quiet and settled stillness is finally restored. The energy that is shed during this final fading ring is immense, more than enough to power a galaxy. But it is just the fading echo of the true crescendo. It is only a tiny fraction of the total, colossal burst of energy that was unleashed in the very instant of the merger. Where did that unimaginable power, that invisible flash brighter than all the stars in the visible universe, truly come from? I would like you to try, just for a moment, to picture the light of every single star in our own Milky Way galaxy, 100 billion suns, all gathered into a single, brilliant point. Then, imagine the light of every star in our neighboring Andromeda galaxy and adding it to that point. Now, continue this, adding the light of all the stars from all the 100 billion galaxies in our visible universe. A cascade of unimaginable brightness, all focused into one blinding cosmic blaze. For the briefest fraction of a second, in the instant that two black holes merge, the energy they release, in a form we cannot see, outshines this impossible cosmic fire. Yet this explosion, the most powerful event the universe has to offer, happens in complete and total silence, and in perfect, invisible darkness. It is not an explosion of matter and light, but an explosion of spacetime itself, a silent, invisible shockwave of pure energy that floods the cosmos in all directions at the speed of light. It is a storm in the very fabric of reality. To understand where this colossal burst of power comes from, we must gently return to the most famous and perhaps most profound equation in all of science, discovered by Albert Einstein: E equals mc squared. Energy equals mass times the speed of light squared. We have spoken of it before, but let us now feel its full weight. The E stands for energy, and the IM stands for mass. The C stands for the speed of light, a value that is already astronomically large, approximately 300,000 kilometers per second. But in this equation, that already huge number is squared. It is multiplied by itself. This results in a number so colossal that it is difficult for the human mind to grasp. What this equation tells us is that mass is not just a property of matter, it is a fantastically concentrated form of energy. Within every tiny atom, within every speck of dust, there lies a locked-up, frozen potential of almost unimaginable power. During the merger of two black holes, the universe turns the key and unlocks that potential with an efficiency that is almost perfect. When scientists analyzed the gravitational wave signal from that first historic detection on September 14th, 2015, they could calculate the masses of the objects involved with remarkable precision. One black hole was about 36 times the mass of our Sun. Its partner was about 29 times the mass of our Sun. If we simply add those two numbers together, we get a total of 65 solar masses. But when they analyzed the final, settled black hole that was born from this union, they found that its mass was only 62 times that of our Sun. 3 whole suns worth of mass were, apparently, missing. That mass was not lost, and it did not vanish. In the violent crucible of the merger, it was converted directly and perfectly into pure energy, the energy that created the powerful gravitational waves that we detected a billion years later. 3 solar masses. The number is simple to say, but the energy it represents is almost beyond comprehension. To put it into a gentler perspective, our own Sun, in its entire 10 billion year lifespan, will convert only a tiny fraction of its total mass into the light and heat that sustains our world. The energy released in this single, fleeting black hole merger, an event that was over in less than 1/5 of a second, was more than 100 times the energy our Sun will produce over its entire 10 billion year life. It was, for that brief moment, more luminous in gravitational waves than all of the stars in the visible universe are in light. The universe, we see, is a place of the most incredible and humbling potential. Matter is not simply the inert, solid stuff we experience in our daily lives. It is a vault, a repository of frozen, locked-up energy from the dawn of time. And the merger of two black holes is the most powerful and efficient process we have ever discovered for opening that vault and releasing its ancient cosmic treasure. This invisible storm of energy fades as it spreads out across the eons and the light years, but it does not leave the universe unmarked. It leaves behind a permanent change, a subtle and eternal memory, etched into the very structure of the cosmos. What are these lasting scars on space-time? Think, if you will, of a powerful and significant memory from your distant past. Perhaps it is the memory of a joyful sound or a moment of profound quiet. The event itself is long over, a ghost of a moment in time, and yet it has not vanished. It has changed you. In a very real and physical way, the experience has subtly altered the neural pathways in your brain, strengthening some connections and weakening others, leaving a permanent trace that helps to define who you are today. The fabric of space-time, in its own grand and silent way, also has a memory. It does not forget the great events that have transpired within it. To help us picture this, let us imagine we are standing on a vast, smooth beach at the edge of the water. The wet sand is perfectly flat. We reach down and draw a deep, clear line in the sand with our finger. A moment later, a gentle wave washes over the shore, smoothing the surface over, erasing the line we have drawn. But has it truly returned the sand to its original state? If we could look closely enough, we would see that the individual grains of sand have been shifted. They have been permanently displaced by our action and by the water's flow. The beach is forever, minutely, different. A powerful gravitational wave passing through a region of space does something very similar. As the main, oscillating part of the wave passes, it causes space to stretch in one direction and squeeze in another, back and forth, like the rising and falling of the ocean wave. But according to Einstein's theory, after the wave has completely passed and space-time has settled down again, it does not return to its exact original state. This is a real, though incredibly subtle, prediction known as the gravitational wave memory effect. It means that the distance between any two free-floating objects in the path of the wave will be permanently, minutely altered. The objects do not return to their starting positions. There is a lasting strain, a permanent offset, an indelible scar left behind in the geometry of space. This is a beautiful and profound parallel to the way memory is physically encoded in our own brains. A process called neuroplasticity. When we learn something new or have a powerful experience, it is not an abstract event. It is a physical one. The connections between our neurons, the synapses, are physically altered. The brain structure is a living, changing record of our journey through life. In the same way, the structure of space-time is a living record of the history of the cosmos. The space we are moving through right now is not pristine and new. It is an ancient landscape, a palimpsest, a document that has been written on over and over again for nearly 14 billion years. It carries the faint, permanent scars of every cataclysmic merger, every supernova explosion, every major cosmic event that has ever happened. Every time two black holes merge, another faint line is drawn in the sand of space-time. We live, then, inside a universe that does not forget. We are floating in an ocean of cosmic memory. The past is not truly gone. Its echoes are woven into the very fabric of the space all around us, a silent testament to the universe's long and dramatic history. And perhaps this reflects our own existence as well. We are, each of us, a tapestry of our memories. We are shaped and defined by the events of our past, by the joys and the sorrows that have left their own permanent, subtle scars on our hearts and minds. They are the invisible geometry that defines the person we are in this very moment. If we are now learning how to read these permanent ancient memories in the fabric of space-time, it opens a gentle door to a new question. Could there be even fainter messages for us to find? Ghostly whispers or strange, fleeting echoes that come not from the violence of the merger itself, but from the even more mysterious edge of the abyss, from the shore of the event horizon. When you stand at the edge of a deep and silent canyon and call out your name, you wait, and a moment later, a faint and ghostly copy of your own voice returns to you. You hear an echo, a reflection of the sound wave bouncing off the distant rock wall. It is a beautiful and simple dialogue with the landscape. Now, let us ask a strange question. What if you could shout with gravity at a black hole? What if you could send a powerful gravitational wave toward that perfect, dark sphere? Our classical understanding, the theory of general relativity that has guided us so well, gives a clear and simple answer. You would be met with perfect, eternal silence. The event horizon is a one-way door, a surface that perfectly absorbs everything that touches it. Nothing, not even a tremor in space-time, should ever come back out. But what if, in the deepest and strangest corners of physics, that is not the complete story? What if, something whispered back, let us place ourselves back in the role of the cosmic listener, our gravitational wave observatory waiting in the quiet aftermath of a merger. We have heard the loud, soaring chirp of the inspiral. We have heard the final, pure ring of the ring down as the new black hole settled. According to the theory, the performance is over. The silence should be absolute. But imagine, after a few moments of quiet, our incredibly sensitive instruments detect another, impossibly faint signal. And then, a few moments after that, another one, even fainter still. They're like ghostly reflections in a hall of mirrors, each one a distorted, fading copy of the final ring-down tone. This is the tantalizing and speculative idea of gravitational wave echoes. To understand where this beautiful and strange idea comes from, we must gently touch upon one of the deepest and most profound puzzles in all of modern physics, the black hole information paradox. The laws of quantum mechanics, which govern the universe on the smallest of scales, are built on a bedrock principle. Information can never be truly destroyed. The unique identity of any object, the story of what it is and where it has been, cannot simply be erased from the universe. But a black hole, according to general relativity, seems to do exactly that. If you throw a book into a black hole, the story, the words, the information, all seem to be lost forever behind the event horizon. This is a fundamental contradiction between our two greatest theories of the universe, and it tells us that our understanding is still incomplete. As a potential solution, some physicists have proposed that the event horizon may not be the simple, smooth boundary we have imagined. Perhaps exotic quantum effects, which we do not yet understand, turn it into something more complex, something akin to a quantum firewall or a strange, reflective surface that is not perfectly absorbent. If this were true, then the powerful gravitational waves from the ring down, as they try to escape, might partially reflect off this quantum structure at the event horizon. A small part of the wave would get out, but another part would bounce back inward, only to be reflected again, leaking out a little more of its energy each time. This would create the series of faint, decaying echoes that our hypothetical observatory detected. Now, it is so important to say that this is the very frontier of our knowledge. These echoes have not been definitively discovered, and the idea itself is still a topic of gentle but serious debate among scientists. It is a beautiful possibility, not yet a proven fact, but its true value lies in how it illuminates the scientific process itself. It shows us how we are using these incredible new observatories not just to confirm what we already know, but to probe the great, unanswered questions, to test ideas that live in the mysterious borderlands, where gravity and quantum mechanics must one day meet and be reconciled. The greatest leaps in our understanding often begin, not with a clear and shouted answer, but with the faintest of anomalies, an unexpected echo in a place where there should have been only silence. Science is a continuous and humble journey into mystery, driven by the courage to listen for the whispers. But whether it echoes or remains silent, the main event is now complete. The merger is over, and a new, singular, and more massive entity has been born from the union of two. What does this process of cosmic growth, of two becoming one, signify for the story of the universe at large? In our human stories, we often think of a marriage not as the ending of two individual lives, but as the beginning of a new, shared one, a new entity with its own unique identity and its own path forward. In the cosmos, the same beautiful truth can be found. The merger of two black holes is not just a conclusion, it is, more profoundly, an origin story. It is a new beginning. As the final ring down fades into the silence of space, let us contemplate the new being that has been born. Where there were once two separate centers of gravity, two distinct entities on their own lonely paths, there is now one. It is a single, massive black hole, now settled and serene in the aftermath of its violent birth. It is larger than either of its parents, its gravitational influence extending further out into the cosmos, a more powerful anchor in its region of space. Its spin is no longer the simple spin of one body, but a complex and elegant combination of the spins of the two original black holes, plus the immense angular momentum of their final, frantic orbit. It is a new gravitational heart, a new center of power, around which new cosmic stories may one day unfold. This act of creation, as chaotic as it was, is not random. It is governed by some of the most fundamental and elegant laws of our universe, the laws of conservation. The final mass of the new black hole is precisely what you get when you add the masses of the two original black holes and subtract the mass that was converted into the energy of the gravitational waves. The final spin is precisely what you get when you combine the original spins and the orbital momentum and subtract the momentum that was carried away by those same waves. The universe, even in its most extreme and violent moments, is not arbitrary. It is a place of profound order and perfect accounting. Nothing is ever truly lost. It is only transformed, and this process of transformation is not necessarily a one-time event. It is repeatable. This new, larger black hole can now continue its own journey through its galaxy. And over the course of cosmic time, it may find another companion, perhaps another lone wanderer like itself, or it may sink into a dense star cluster and find a new partner there, and it can merge again. This process is known as hierarchical merging. It is a step-by-step construction project, a way for the universe to build ever larger and more massive black holes from smaller, simpler components. In this process, we can see a beautiful and powerful parallel to the story of life itself on our own planet. For billions of years, life on Earth consisted only of simple, single-celled organisms, like bacteria and amoebae. But then, through processes of cooperation and combination, these simple cells began to merge, to form more complex, multicellular life. This was a revolutionary leap, leading to the incredible diversity of plants and animals we see today. The universe, it seems, uses this pattern of construction on every scale. On the cosmic scale, simple, stellar mass black holes, born from the death of single stars, merge to create larger, more influential objects. It is a universal theme, a deep and resonant pattern of growth. Simple components combine to form more complex systems, which in turn have new and more powerful capabilities. This reveals to us a deeper truth about the cosmos. The universe is not just expanding and cooling, a story of slowly fading energy. In pockets of high density, in the hearts of galaxies, it is also actively building. Through processes like these mergers, it is creating structures of ever-increasing scale, influence, and gravitational complexity. It is a story of cosmic construction, a story of growth and evolution, unfolding over the slow and patient timescale of billions of years. And this grand construction project is not just happening in the lonely, dark spaces between the stars. This very same process, this patient, hierarchical merging, is believed to be the primary engine that builds the largest and most foundational structures we know, the very galaxies that house and nurture the stars. At the very center of our own beautiful, sprawling Milky Way galaxy, and at the heart of nearly every other large galaxy we have ever observed, beats a quiet and invisible heart of unimaginable mass and density. It is a supermassive black hole. It is the gravitational anchor around which our entire city of 100 billion stars revolves. But it was not born this way. It was not created in a single mighty explosion. It was built piece by piece over the entire age of the universe. To understand how is to understand that the dance of two merging black holes is not just an isolated event, but a fundamental process of cosmic construction. Let us take a gentle, imaginary journey to the heart of our galaxy. As we travel inward from our quiet, suburban spiral arm, the view begins to change. The sparse scattering of stars becomes a dense river, then a blinding ocean of light. The sky is no longer black, but is filled with a soft, golden haze, from the light of millions of ancient, closely packed suns. And as we get closer to the very center, we notice the stars are moving with an incredible frantic speed, swarming like brilliant bees around an invisible hive. They are tracing out tight, elliptical orbits, held in place by the gravity of something we cannot see, something with the mass of 4 million of our suns, all packed into a region smaller than the orbit of Mercury. This is the domain of Sagittarius A star, our galaxy's own supermassive black hole. These are the titans of the cosmos, weighing millions, or in the case of larger galaxies, billions of times the mass of our Sun. Where they came from is one of the most compelling and active questions in all of astronomy. The leading theory, the story that seems to fit the evidence best, is that they grew through a long, patient chain of mergers, in a process that mirrors the hierarchical merging we have already discussed. The story likely begins in the dawn of the universe, with the very first generation of stars, which were thought to be much more massive than the stars we see today. When these giants died, they would have created the first seed black holes, perhaps 100 times the mass of the Sun. These seeds, adrift in the dense, early universe, would have grown, partly by consuming the rich gas around them, and partly by finding and merging with each other. And as they grew, their host proto-galaxies grew around them. The next, and most crucial, step in this construction project happens when entire galaxies collide. As two galaxies merge, their central black holes, each now millions of times the mass of the Sun, begin their own slow, majestic spiral toward the new center of the combined galaxy. This is the same cosmic waltz, the same in spiral and merger, that we have been exploring, but on a scale of almost unimaginable grandeur. And the process repeats. This newly merged, even more massive black hole will one day find itself on a collision course with another, when its new, larger galaxy merges with another. It is a story of cosmic consolidation, of smaller structures combining over eons to form the great, mature galaxies we see today. But the relationship is even deeper than that. The galaxy is not just a passive home in which the black hole grows. The two, it seems, grow together, in a delicate, cosmic feedback loop. We now believe that galaxies and their central black holes co-evolve. When the supermassive black hole is actively feeding on a large cloud of gas, it can release a colossal amount of energy back into the galaxy in the form of powerful jets of particles and intense radiation. This blast of energy can be so powerful that it heats up the gas throughout the galaxy and can even blow it out into intergalactic space. This effectively shuts down star formation in the galaxy for a time, because the cold gas needed to form new stars is gone. The black hole acts as a kind of cosmic thermostat, regulating the growth of its own home. And in this, we find a sense of profound interconnectedness. The beautiful, spiral structure of our galactic home, the rate at which its new stars are born, and its ultimate, quiet fate, are all intimately and inextricably tied to the silent, invisible life cycle of the giant at its heart. The universe is a deeply nested system. The small-scale physics of two black holes embracing in the dark dictates the large-scale architecture of a city of 100 billion stars. If these mergers, then, are so fundamental to the very structure and story of the galaxy we call home, what does that mean for us? Creatures of stardust, living our quiet lives on a single, small planet, orbiting a single, average star. How are we, in our own small and fragile way, connected to these distant, silent, and unimaginably powerful embraces? You have likely heard, at some point in your life, the beautiful and poetic phrase, "We are all made of stardust." And this is a profound and literal truth. But tonight, let us add a new and even deeper layer to this truth. We are not only the children of the stars, we are also the children of spacetime storms. Our existence is a direct consequence of the great cosmic dramas of stellar death and gravitational union that we have been so gently exploring. To feel this connection, I invite you to bring your awareness, just for a moment, to your own physical presence. Feel the gentle warmth of your body, the quiet, steady rhythm of your own heart beating. Think of the iron atoms in the hemoglobin of your blood, the very atoms that are carrying oxygen through you right now, allowing you this moment of quiet life. Think of the calcium that gives strength and structure to your bones. Where did these atoms, so essential to our being, come from? If we trace their history backward, we find a story of incredible antiquity. They were once in the food we ate, and before that, in the soil of the earth or the water of the oceans. Before that, they were part of the swirling cloud of gas and dust from which our sun and all its planets formed 4.5 billion years ago. And before that, they did not exist. They were forged, created, in the impossibly hot and dense core of a massive star that lived and died long before our sun was ever born. This process, stellar nucleosynthesis, is the universe's primary alchemy. All of the elements heavier than hydrogen and helium, the carbon that forms the basis of our cells, the oxygen we breathe, the iron in our blood, were created inside the hearts of these giant stars. And they were scattered across the galaxy in the star's final, glorious acts. The supernova explosions. These are the very same explosions that, as we have learned, give birth to stellar mass black holes. The death of a star is therefore a dual act of creation. It creates both the seed of ultimate collapse, a black hole, and it scatters the seeds of future life, the heavy elements, across the cosmos. But having the raw materials is not enough. To build a house, you need not only bricks and mortar, but also a stable foundation and a blueprint. In the cosmos, the raw materials are the elements, and the foundation is the galaxy itself. And what sculpts and organizes the galaxy? What provides the stable, gravitational framework that allows those clouds of enriched gas and dust to cool, to collapse, and to form new generations of stars and planets? As we have just discovered, the very structure and evolution of our galaxy are intimately linked to the life cycle of black holes, and especially to the growth of the supermassive heart at its center through an endless series of mergers. The gravitational framework of the universe, held together by the invisible scaffolding of dark matter, but shaped and regulated by the mergers of black holes, is what allowed our own solar nebula to gather in a quiet, stable spiral arm in the first place. Without the galaxy, there would be no solar system. Without the supernova, there would be no heavy elements. Without the star, there would be no supernova. And so, we can see an unbroken causal chain, stretching back across the eons, that connects us directly to the events we have been exploring. The Big Bang created the simplest elements. The first stars forged them into heavier ones. Those stars died, creating black holes and scattering the precious, life-giving elements into space. The mergers of those black holes, over billions of years, helped to build and shape the galaxies, providing the stable homes required for new stars and planets to form from that enriched material. And on at least one of those planets, under the gentle light of a second-generation star, life emerged. We are not, therefore, merely separate observers looking out at the universe. We are a physical manifestation of the universe's long and interconnected history. The very laws of gravity that orchestrate the final, frantic dance of two black holes a billion light-years away are the same laws that bind the atoms in our own bodies and keep our feet gently planted on the earth. We are a part of this cosmic story, a living, breathing testament to its creative and destructive power. After the cataclysm, the ring down, the shaping of galaxies, and the seeding of life, what is left? What is the final state of the object at the very heart of our story? It is a state of profound, deep, and nearly eternal silence. In our world, every sound, no matter how loud or how beautiful, eventually fades into the quiet hum of the background, and then into a deeper silence. In our cosmos, every storm, no matter how vast or how violent, eventually spends its energy and finds its calm. The final state of a merger, the ultimate fate of this grand and dramatic story, is a perfect, profound, and nearly unending stillness. In the aftermath of the ring down, as the last faint gravitational wave whispers its way across the universe, what is left is a single, solitary black hole, resting in the quiet dark. Let us take a moment to visualize it. It is no longer a part of a dynamic, dancing pair. It no longer emits the powerful waves of a violent merger. It simply is. It hangs in space, a perfect sphere of darkness, its immense gravity holding a serene and silent court. It is a monument to the fiery embrace that created it. It is an icon of perfect, massive, and peaceful equilibrium. This state of quiet seems, for all intents and purposes, to be eternal. A final, unchanging feature of the cosmic landscape. And yet, in the strange and beautiful world of theoretical physics, we find a hint that even this profound stillness may not last forever. The great physicist Stephen Hawking, by combining the laws of gravity with the strange rules of quantum mechanics, made an astonishing discovery. He found that, due to subtle quantum effects that constantly happen at the very edge of the event horizon, a black hole should not be perfectly black. It should emit a faint, constant, and incredibly weak trickle of particles. This phenomenon, now known as Hawking radiation, means that a black hole is not a perfect prison. It has a very, very slow leak. And because it is constantly losing a tiny amount of energy and mass in this way, it must, over unimaginable timescales, eventually evaporate completely. This idea connects our story to the possible ultimate fate of the entire universe. Some cosmologists theorize about a distant future they call the heat death of the universe. This would be an era, trillions upon trillions of years from now, when the last star has burned out and gone dark. All the matter in the cosmos will have decayed, and all that will be left is a cold, dark, and ever-expanding sea of low-energy particles and faint radiation. In this final, quiet chapter of the cosmos, the last remaining structures will be the black holes, and they too, through the slow, patient process of Hawking radiation, will eventually evaporate, one by one, until nothing is left but a uniform, near-empty void, at a temperature just fractions of a degree above absolute zero. But this timescale, the time it would take for a black hole to evaporate, is a number so large that it defies human language and human imagination. A black hole the mass of our sun would take longer than the current age of the universe, raised to the power of 54 to disappear. For the supermassive black holes at the hearts of galaxies, the timescale is so vast it is, for all intents and purposes, a true eternity. So, for now, and for trillions upon trillions of years to come, the single, merged black hole represents a kind of perfect permanence. It is a quiet monument to the fiery dance that created it, a silent keeper of the mysteries within its horizon. And in this final silence, we can find a gentle reflection for our own lives. We so often live in a world of constant noise and motion. But in seeking moments of stillness, in finding a quiet space to simply be, we allow for a different kind of process. A process of reflection, of integration, and of peace. The universe itself, on the grandest of all scales, also trends toward this quiet, high-entropy state. Perhaps, then, silence is not an emptiness to be feared. Perhaps it is a state of profound fullness, a final, settled completion. And as we gaze into this final, silent state, in the deep peace of this moment, we are left looking at the ultimate mystery, the question that began our journey and remains unanswered at the very end of it. What lies beyond that silent, dark horizon? Every great journey of discovery, whether it is across an ocean or into the heart of an atom, ends not at a final, absolute destination, but at the shore of a new and much larger ocean of questions. And so, as our own gentle journey comes to its close, we find ourselves standing at the edge of that ocean, looking out into a beautiful and profound mystery. Let us take one last, quiet look back on the path we have traveled together tonight. We began with the feeling of gravity, not as a force, but as the gentle curvature of a cosmic trampoline, the soft fabric of spacetime that holds us all. We witnessed the last, shuddering breath of a dying star, an act of destruction that was also an act of magnificent creation, giving birth to a new black hole. We imagined two of these lonely wanderers, finding each other in the dark, beginning a slow and graceful waltz that would last for eons. We listened, with our mind's ear, to the sound of their union, a rising cosmic chirp that has travelled for 1 billion years to tell us its story. We saw them touch, a silent merging of two horizons into one trembling, unified whole. We felt the calm of the ring down, as the new entity settled into a serene and perfect stillness, a final, silent monument in the cosmic dark. We have answered the question we began with. Can two black holes merge? The answer, we now know, is a clear and resounding yes. We have heard their song. But this simple, beautiful answer has not closed the book. It has opened it to a chapter of even deeper, more wondrous questions. We are left to wonder, for instance, what truly lies at the very center, hidden forever behind the veil of the event horizon. Our current theory of gravity predicts a singularity, a point of zero size and infinite density, a place where the laws of physics as we know them break down completely. Is this the reality? Or, as many physicists now believe, will a new, deeper theory, a theory of quantum gravity, resolve this impossible infinity into something else, something even stranger and more wonderful? Perhaps it is a fuzzball of vibrating strings of energy, or a Planck star, an object of incredible but finite density. We simply do not know. And what of the more fantastical ideas that these objects inspire? Could a black hole be a gateway, a bridge through space-time to another point in our own universe, or even to another universe entirely? This is the idea of a wormhole, a beautiful and compelling concept that emerges from the mathematics of relativity, but for which we have absolutely no physical evidence. Are there cosmic opposites, objects known as white holes, from which matter and energy can only exit but never enter? These remain the beautiful deep dreams of physics, tantalizing possibilities that inspire our curiosity, but still live in the realm of gentle speculation. What we do know for certain is that our journey of listening to the universe has only just begun. We have only been able to hear these gravitational waves for a few short years. In the coming decades, new observatories, both on Earth and in space, like the planned Laser Interferometer Space Antenna, or LISA, will allow us to hear the universe with a clarity and a sensitivity that we can only dream of today. We will hear the low, rumbling bass notes of supermassive black holes merging at the hearts of distant galaxies. We will surely find answers to some of our questions. But far more importantly, and far more beautifully, we will undoubtedly discover new mysteries, new songs, and new questions that we cannot yet even imagine. And this, perhaps, is the true, gentle gift of science. It does not seek to strip the mystery and the wonder from the cosmos. It seeks to replace a simple, unexamined mystery with a far more profound, intricate, and beautiful one. It does not just give us answers to hold on to, it gives us ever more magnificent questions to dream about. And so our story ends here, on the shore of that quiet, cosmic ocean, with a sense of peaceful, open-ended wonder. The answer to our question is yes, and that yes has made the universe a far more magical and musical place than we ever knew. Thank you for joining me on this journey tonight. I hope it has brought you some small measure of peace, of comfort, and of wonder. May your sleep be deep and restful, and may your dreams be filled with the gentle light of distant stars. If you have found a moment of quiet in our time together, I would be so grateful if you would subscribe to the channel for more soothing stories from the heart of science. Until next time, I wish you a very soft and very peaceful good night.